My name is Muhammad Aziz Dawisi bin Wesley, matrix number 24 DKM 24 F1016.
Okay, my name is Muhammad Ashraf bin Muhammad Ismail. My matric number is 24 DKN 24 F1022.
My name is Saravanan Analaki Ranganathan. My matric number is 24 DKM 24F 1061.
Good morning, sir. My name is Nirudia Firzana F1019. Today, I'll be presenting our automated hydroponic farming system. The goal is to solve key challenge in water circulation, nutrient delivery, and environmental stability, ensuring sustainable plant growth. Okay, firstly is the problem identification. In hydroponic farming, consistency is critical. Manual monitoring or basic controller often fail to provide reliable performance, leading to uneven growth and higher risk of crop failure. The main issues are inconsistent water circulation. Second, inaccurate nutrient dosing. Third, unstable pH control. Lastly, safety concern. Next is automate solution. To address this challenge, we propose a PLC controller automate solution. The circulation pump ensures constant flow, eliminating stagnation. The nutrient dosing unit, using solenoid valve and timers, delivers precise volume at scheduled interval. The pH control subsystem continually monitoring acidity and alkalinity, automatically adjusts the level for optimal absorption. Safety features are embedded in the PLC logic. First, low-level water sensor prevent pump from running dry. Flow sensor detect blockage or failures. Temperature sensor monitor water condition to prevent overheat. Together, these functions enhance efficiency, reduce human error, and ensure long-term sustainability. Next is the key component. The system integrates several critical components into the PLC framework. First is water level sensor, flow sensor, and temperature sensor. Second, circular pump and neutral pump. Third, pH up and down pump. 4. Alarm indicator for valves. 5. PLC hardware and CX programmer software to execute ladder diagram and coordinate all subsystems. Next is system operation. Here how the system works step by step. First, reservoir level monitor, which is float sensor check water level. If low, pump shut off to prevent damage. Second, circulation pump activation. When levels are sufficient, the pump runs continually, prevent stagnation and ensuring even nutrient distribution. Third, nutrient dosing cycle. Solenoid valve and timers inject nutrient precisely, reducing waste and avoid imbalance. Fourth, pH sensor feedback and correction. Sensor monitor acidity in real time. Corrective pump adjusts automatically to maintain optimum condition. Lastly, flow and temperature safety, where flow meter detect blockage, while thermocoolers track water temperature. Alarm or shutdown between protect crop and equipment. The next is the benefits. This automated system delivers multiple benefits such as efficiency, optimal water and nutrient delivery, reduce waste, and maximize growth. Next is safety sensor and monitoring protect pump valve and crops. Third is reliability. PLC logic ensure consistent operation and reduce downtime. Scalability, modular design allow expansion for large system. Next is error reduction. Automation minimize human mistake in monitoring and adjustment. Next is sustainability. Efficiency, resource use, super eco-friendly farming, and lower cost. Last, industry 4.0 alignment, integrate automation, sensor feedback, and data-driven control for smart agriculture.
For section 3.0, I will explain the PLC programming used in the smart hydroponic system. The system is programmed using mnemonic instruction list in CX programmer. 3.1 Input and output table. The system uses several input and output, include the start button, stop button, emergency stop, water level sensor, flow sensor, and reset button. And for the outputs, it include the water pump, nutrient pump, pH control pump, and indicator. 3.2 Ladder diagram. I will explain how the system operates starting from the start push button is pressed. When the start push button is pressed, the input 0.00 become on. The PLC first check the safety conditions. It ensures that the stop button is not pressed, the emergency stop is not active, and there is no fault in the system. If all conditions are safe, the system is latched into run mode, which is stored in W0.00. This means the system continue running even after the start button is released. When auto mode is enabled, the PLC activates dosing the circulation function, allowing the system to operate automatically. Next, the system starts the water circulation process. A timer delay is applied, and after the delay, the water pump is turned on to circulate the nutrient solution. If the EC level is low, the PLC activates nutrient pump A and pump B to restore the correct nutrient concentration. The system also controls the pH level. If the pH is too high, the pH down pump is activated. If the pH is too low, the pH up pump is activated. During operation, the PLC continuously monitor water level, flow, and temperature to ensure safe condition. If any abnormal condition is detected, the system will stop immediately and the corresponding alarm will be activated. The system can only be restarted by pressing the reset button when all conditions return to normal. They ensure the system operates automatically, efficiently, and safety at all times. 3.3 Mnemonic table. The program is written using mnemonic instructions such as LD, and not, or, and out. This instruction process input conditions and control outputs. For example, LD loads a condition and combine condition, and out activate an output. 3.4 Flowchart. The system flow start with the start button, followed by safety checking. If conditions are safe, the system runs and continuously monitors sensor. If any fault occur, the system stops and activates alarm. 3.5 Working principle. The PLC continuously reads sensor inputs such as water level, flow, and temperature. Based on these inputs, it automatically controls the water circulations, nutrient dosing, and pH adjustment. If any abnormal condition is detected, the system stops and activates alarm. The system can only be reset when all conditions return to normal.
Okay, we're going to chapter 4, implementation plan. This section outlines the strategic step for transitioning the manual or microcontroller-based system to the sustainable PLC-based architecture. Okay. Troubleshooting procedure. To ensure system reliability and minimize environmental impact due to equipment failure, the following troubleshooting steps are established. Okay, for the table, first component, float or level sensor. For the continual issue, false low level signal. For the troubleshooting action, check for sensor obstruction or wiring corrosion to ensure accurate water conversion. conservation. Okay. Next, circulation pump failure to activate. We must inspect PLC output LED, verify 24-volt signal and ensure idle detection. Logic is not stuck in shutdown mode. Okay, next, pH or nutrient sensor. Inaccurate feedback. We must calibrate sensors using standard buffer solution to prevent chemical waste from overdosing. And lastly, PLC controller, logic hang or stop mode. We must check status indicator, verify power supply and re-upload the sustainable ladder logic if necessary. Okay, we're going to chapter 5, project documentation. This chapter provides a comprehensive technical record of the system architecture, sustainability, control strategies, and engineering standard compliance implemented in the transformation of this project. Next, system control architecture. The documentation details the integration of hardware and software to ensure the system operates at maximum energy efficiency. Firstly, PLC logic integration. The ladder logic is documented to support low power modes where non-critical outputs are deactivated when sensor detects zero activity. Next, sensor calibration records. Procedures for calibrating pH and level sensors are recorded to ensure high precision inputs, preventing the waste of waters and nutrients due to reading errors. And lastly, I/O interfacing. Documentation of connection between input sensors and output devices like pumps, valve and actuator is organized to facilitate real-time energy flow monitoring. Next, sustainable control strategy documentation. The core strategy documented in the shift from a manual or continuous system to a demand-driven PLC architecture. First point, demand-driven logic. The system is activated strictly based on feedback from reservoir level fluid sensors. This ensures the circulation pump only runs when necessary. Next, nutrient dosing precision. Timers and counters within the PLC logic are utilized to ensure precise nutrient injection circles, significantly reducing chemical runoff and environmental pollution. Lastly, idle detection protocols. Documentation outlines the automatic shutdown parameters with power down the system during prolonged periods of inactivity to conserve electricity. Okay, next, safety and ethical compliance record. As part of the social responsibility of engineers, this documentation addresses safety and ethical consideration. Okay, first point, safety interlocks. Documentation of safety logic where the PLC triggers an emergency shutdown and an alarm if flow failures or unsafe conditions are detected. Next, environmental impact statement. A technical report on how this system contributes to a reduced carbon footprint through optimized energy consumption at polytechnic Banting. And lastly, regulatory alignment records showing the system's design complies with documented engineering codes of practice and environmental regulation. Okay. Lastly, maintenance and life cycle management. This documentation provides guidelines to maintain system efficiency over its long-term operational life. Firstly, preventive maintenance log, a schedule for product inspection to verify pipe integrity and ensure pump motors are operating at peak efficiency. Lastly, a standard operating procedure or SOP clear work instruction for operators to prevent unnecessary energy during system setup, cleaning or maintenance phase.
Moving on to 6.0 Testing and Evaluation. The PLC based automated hydroponic tower system was tested to see how well it performs, how efficient it is, and how reliable it is compared to the manual version. The purpose of the test was to check if the system can automatically maintain the best condition for plant growth using real-time monitoring and control. Important factors like water level, nutrient concentration, pH level, and surrounding environmental condition were measured to see how efficient the system is. The test also looked at how much energy the system uses, how fast it responds to changes, and whether it operates safely. Next, we have 6.1 Objective of the solution. The main objective of the PLC based hydroponic tower system are to automate nutrient dosing and irrigation processes for improved efficiency, to ensure accurate and consistent control of water quality parameters, to reduce manual intervention and human error, to improve energy efficiency and resources utilization, to enhance system reliability and operational safety through alarms and interlocks, to enable scalability for larger agricultural applications. After that, we have 6.2 Test criteria and features. The system was evaluated based on the following criteria. First one, input and output verification. Sensor like water level, pH, EC provide accurate real-time data. PLC correctly processes input signal and execute control logic. Actuator like pumps alarm respond appropriately. Second, functional testing. Automatic activation of pumps when water level drops. Precise nutrient dosing based on EC readings. pH adjustment within optimal range. Alarm activation under abnormal condition. Third, performance indicators. Stability of nutrient solution over time, response time of system adjustment, and continuous operation without failure. For summary table, the parameters are water level, EC level, pH level, and system fault. For the water level, the condition is low level detected and the result are pump activate automatically. For the EC level, the condition is below threshold and the result are nutrient pump activated. For the pH level, the condition is out of range and the expected result are adjustment process triggered. And lastly, for the system fault, the condition is pump failure and the expected result are alarm activated. For 6.3 Test procedure and evaluation criteria. Test procedure, the first step is initialize the PLC system and ensure all sensors are calibrated. Second one is fill the reservoir with nutrient solution. Third is simulate different conditions for reduce water level, alter EC and pH values, introduce system fault. Fourth step is observe system response for pump activation, nutrient dosing, and alarm triggering. Fifth is record system performance over a fixed period. For the evaluation criteria, the system performance was evaluated based on accuracy, ability to maintain correct EC and pH level. Second, response time, speed of system reaction to changes. Third, reliability, continuous operation without breakdown. Fourth, efficiency, reduction in water, nutrient and energy usage. Fifth is safety, proper functioning of alarm and interlock. Next, I will explain 6.4 the risk and mitigation method in our system. First one, sensor failure. If the sensor fail, it may give incorrect reading and affect the system. To solve this, we do regular calibration and use backup sensor. Number 2, pump malfunction. If the pump stop working, water circulation will stop, so we use a backup pump and and alarm system. Third, power failure. If there is a power cut, the system will shut down. To prevent this, we use a UPS or backup power supply. Fourth, overdosing nutrient. Too many nutrients can damage the plant. The PLC control this by setting limit and using safety logic. Fifth, water leakage. Leakage can cause resource loss and reduce efficiency. We prevent this with proper sealing and regular maintenance. So by identifying these risks and applying the right solution, our system becomes safer, more reliable and efficient. Next, I will explain 6.5 success metrics of our system. Firstly, efficiency improvement. Our system reduces water and nutrient waste by around 20 to 30%. It also uses less energy because the pump operation is optimized. Second, system performance. The system has a faster response time compared to manual control. It can also maintain stable pH and EC level within the optimal range for plant growth. Third, reliability. The system can run continuously with minimal human intervention. It also reduces downtime because monitoring is done automatically. Fourth, sustainability impact. Our system supports environmental friendly farming. It also reduces carbon footprint by using resources more efficiency. Overall outcome. Lastly, overall outcome. Overall, the PLC based hydroponic tower shows clear improvement compared to the manual system in terms of overall outcome. Overall, the PLC based hydroponic tower shows clearly improvement compared to the manual system in terms of automation, efficiency, scalability and sustainability. It meets all design objectives and is suitable for both education and commercial use.
Lastly, this is the conclusion and recommendation. The PLC control hydroponic tower proves that automation can make farming more efficiency, reliable and sustainable. By combining water circulation, nutrient dosing, pH regulation and safety monitor into one system, it ensures consistent plant growth while reducing human error. The project also gave students value hands-on experience in PLC programming and troubleshooting, linking to theory with practice. The key benefits include optimized nutrient delivery, safety interlock, modular scalability, reduced waste, fewer mistakes, and alignment with the Industry 4.0. Looking ahead, integrating SCADA for remote monitoring, IoT sensor for real-time data, and scaling for commercial use will strengthen the system further. Overall, the hydroponic tower is smart, eco-friendly solution ready to involve the prototype to commercial farming. That's all from us. Thank you.